In this video, I'm going to go through the Edexcel A-level Chemistry paper. This is paper 1 from June 2019. This is the second half of the paper. I covered the first half in an earlier video. So here we go on question 7. Okay. Right. This is a long, wordy question, sort of question I don't like doing. Color is often used in chemistry to identify substances, compare and contrast the origin of the color of a copper complex, copper 2 complex. Let's write that, doesn't it? Copper 2 complex, a complex ion, with the origin of the copper 2 in a flame test. Okay. So let's obviously you would have to write it in prose. I'm going to do a little table here, maybe. Right. So first of all, the big difference in here with the flame test is that you get color because light is emitted. Whereas, of course, the color of a copper 2 complex, like copper 2 ions in an aqueous solution, for example, the reason why that is colors is because you get absorption of certain frequencies of white light. Stands for frequency, by the way. So white light is a mixture of all the different frequencies of visible light. And for example, copper 2 tends to looks blue, and that's because the solution, the ions are absorbing other colors except blue. And it's only the blue light which is allowed to be transmitted, that goes through the solution. So e.g. is going to absorb red light, red frequencies, so it appear blue. And that is different to the flame test situation. So here, the copper flame test, it looks green. You don't say what color, and it looks a certain green because it emits light of certain frequencies, and it looks that color. So it's emitting green light, and the flame looks green. Okay, now what is causing the in this case the absorption? All right, what causes the absorption of the light? And that's because electrons absorb the energy and being promoted to a higher energy orbital. And we'll talk about which orbital that is in a minute. Whereas in this case, in the case of the flame test, the electrons they're in an excited, or electrons are already in the higher energy orbital because of absorbed heat energy, or the energy for that has come from the heat. And when they return to the lower energy, the excess energy is emitted as light. And you might want to mention the energy is given by the equation. E is equal to Planck's constant h multiplied by the frequency. Okay. Now we need to talk about, that's probably got a sort of large chunk of the marks, but we need to talk about in the complex, what is the electrons are promoted from one lower energy orbital to a higher. What are those energy orbitals? Okay, and the electrons are promoted from one d orbital to another, but we need to say that the d orbitals are the same energy. There's 5 of them. They're all the same energy. But when you bind ligands, this so-called degeneracy, in other words, they've got the same energy. When they bind ligands, the degeneracy of the orbitals is lost. Two of the d orbitals go higher, slightly higher in energy. And 3 go slightly lower. Okay, and the light that is being absorbed is the energy promotes an electron from a lower d energy orbital to a higher one. Okay, so I think that will probably be enough for that question. Okay. Okay, sodium hydride here can be used to generate hydrogen for fuel cells. Sodium hydride, sorry. In order to calculate the first electron affinity of hydrogen, a student was asked to draw a Born-Haber cycle. The cycle had 2 errors, but the numerical data were correct. So let's have a look at this cycle and where the 2 errors are. Okay. Now, see, the first error is here. Right. This is the enthalpy change of formation here. Now, the enthalpy change of formation, the arrow should be going in the other direction, because, of course, it's when you form an element, when you form a compound, that's the compound from the elements in the standard state. So we've got the arrow go the wrong way around there. So that's the first error. And that's why you've got a minus sign there, because the arrow is going down. It's an exothermic change. So that's the first error. The second error is this one up here. Okay. It says half the energy enthalpy change of atomization of hydrogen. Okay, what have they done here? They've got half of a molecule of hydrogen, and they've half of a mole of hydrogen, and they've split it into gaseous hydrogen atoms. Well, if you look this way, it's important to know the definitions for the Born-Haber cycle. Delta H hat, the atomization energy, is defined as the enthalpy change occurring when 1 mole of gaseous atoms are formed from the element in a standard state. In other words, it's this one here. You're forming 1 mole of hydrogen atoms there. Here, you're not forming 1 mole of hydrogen atoms, you're forming 2 moles. So that's not it. Okay. Okay, so after you change the one there is that, yeah, that 218 kilojoules per mole refers to 1 mole of hydrogen atoms, not the molecules. Okay. Okay, next part of the question, the equation for the formation. Okay, or what we need to do now, sorry, is we need to calculate, which is part 2. So that it asks us to calculate the first electron affinity. Okay, that's what we've got to find out. We've got to calculate the first electron affinity of hydrogen. So in other words, we've got to find out the value of that arrow I've just drawn in green there. So what we need to do is we need to find out how big that green gap is by adding up all of these, and we won't worry about the signs. So we've got to add up all these ones in red on the left here. Don't worry about the signs. That's why you draw it as a diagram, really. Just add those numbers together. So we've got to add 218, 496, 107, and 56 together, not worrying about the signs, take them all as positive. So that gives us That gives us 877 kilojoules on that side. Right, and then this yellow arrow here, the lattice enthalpy, right, that's 804. So the green one is the first electron affinity, is going to be equal to the red one, 877. And again, I'm not worrying about signs again here, minus the 804. And that gives us a value of 73 kilojoules. Now we do have to now decide what the sign is. And the way you could decide what the sign is, well, look, the arrow there is going down. So the arrow is going down, it is exothermic, so the sign is negative. So that is the way I would do that there. If you don't like this, me ignoring this minus sign here, I suppose what you could say is, look, it becomes a plus because I've gone against the arrow, haven't I? Because I'm not following the arrow up, I'm following it down. Yeah, okay. Right, next one. The equation for the formation of sodium hydride is that. They give us the entropy change, delta S, and we've got to work out delta G. So we need to know that equation, which is, of course, delta G, and we've got to work out it's feasible. So it's feasible if delta G is negative, is equal to delta H minus T delta S. And what you've got to be careful with here is, look, the units here are joules per Kelvin per mole, whereas that's in kilojoules per mole. So, you know, you've got to convert. I usually convert to kilojoules, so I'm going to turn that into kilojoules. That's going to be minus point divided by 1,000, 0.765 kilojoules per mole per Kelvin. Let's put the numbers in there. So delta G is equal to minus 56 minus 298, which is the temperature, minus 0.0765. That's equal to minus 56 plus 22.8, which is equal to 30 minus 33.2 kilojoules per mole. So it's negative, and so the reaction is feasible. Okay. Right, the sodium hydride is crushed in the presence of water to release the hydrogen gas for a fuel cell. Okay, so this is not talking about sodium hydride really now, it's talking about the hydrogen fuel cell. The equation occurring in the hydrogen fuel cell is simply hydrogen combining with oxygen to form water. Okay, and in alkaline fuel cell, the oxidation half equation, losing the electrons, is that. Okay, and so we've got to deduce the reduction half equation. Right, so which element is being oxidized here? Well, it's hydrogen, because that's going from 0 to oxidation number +1 in water. So that means it must be the oxygen which is reduced. Yeah, let's do that. So the oxygen is oxidation number of 0 there. And of course, the oxidation in water is -2. Now, this is under alkaline conditions. So I'll show you how I would, it's only one mark question, but this is how I would work out the half equation there under alkaline conditions. The way I do it, you may have a slightly different way of doing it. Right, first of all, I would say just normally half O2 is going to H2O. Now, forget that it's in alkaline conditions for the minute. What would we do there? Well, we balance for oxygens, we've got to balance for hydrogens. We normally balance that with H pluses. And then we've got to balance for the the half equation for the charges. So we've got 0 charge on the right, +2 on the left. So we need 2 electrons, 2 E minus there. Now, this is under alkaline conditions, so we can't have H+ ions. So we get rid of them by adding OH- ions, and they're going to turn into water. So add 2 OH- ions to both sides of the equation. Okay, let's do that. So half O2 plus 2H2 plus 2 OH- plus 2 E- goes to H2O plus 2 OH-. Right, so we can get rid of that H+ and OH-, that's going to form 2 waters. So that's plus 2H2O. Now we've got H2O on both sides of the equation, so we can get rid of that H2O and turn that into symbol 2, just one H2O, and that is our half equation. That is the answer we want. That's it there. Okay, that's the way I do it. Whenever you want to convert half equations from acid into alkaline conditions, I usually write them out as they would be in acid conditions first. That's easier. And then get rid of the H pluses by adding the appropriate number of OH minuses. Okay, lattice energies provide an indicator of ionic bond strength. Okay, in other words, when I say ionic bond strength, what is the attraction between the positive ion, X plus, the electricity, what's the strength of that, and the negative ion? How strong is that? Now, what governs the strength of that is, first of all, the charge, the size of the charge. Okay, if that was a 2 plus rather than a 1 plus, obviously it's going to be a much stronger attraction. The other thing that affects it is the size. Now, the closer the ions can get together, the stronger the attraction between the two charged ions. So the size, so it's stronger for smaller ions. Okay, so they've given us sodium hydride. Now, I've drawn the sizes of the ions here on the right-hand side. Now, we know that potassium and sodium, they both got a 1 plus charge, but potassium is bigger because it's one lower down. It's got another shell of electrons. It's lower down the periodic table. So that means the lattice enthalpy potassium hydride has got to be smaller than sodium. So it can't be these. That's wrong, because it's got to be smaller. It's either got to be A or B. Then we have to think about magnesium hydride. Now, magnesium hydride would have a higher lattice enthalpy than sodium hydride, because look, magnesium is a 2 plus ion and sodium is only a 1 plus, so it's going to be way bigger because it's a 2 plus ion. Also, magnesium is also smaller. That will also make it bigger. So the only possible one would be that then. So B is the answer there. So it's all about the attraction between the ions. As I say, the more highly charged they are, the bigger the attraction, and the closer they can get together. In other words, the smaller they are. Okay. Okay, question 9 about buffer solutions. Right, a buffer solution always, that's wrong. It doesn't always keep the pH less than 7. You can have alkaline, you can have any pH buffer. Equimolar acids in its conjugate base, no, they don't have to be in exactly equimolar. Equimolar, that's wrong. Keeps the pH constant to small quantities of acid. No, it doesn't. It will change a little bit, just not much. This is the one. It resists changes in pH. That is the correct answer. Now here's question 5, which is quite a tricky calculation. It's 5 marks. Sorry, question B. Right. You want to make a buffer solution of pH of 3.9. Right. Calculate the mass in grams of sodium ethanoate. So sodium ethanoate, I'll write down as Na plus A minus. That should be added to the ethanoic acid. Let's write that down as HA to form this buffer solution. Right. So how are we going to do this then? What I would do is, first of all, write down the equation for Ka, which I've written down there. And then I would rearrange that to get the concentration of sodium ethanoate here, divided by the concentration of ethanoic acid, is equal to Ka times H plus. And now we need to start putting some numbers in. Before we do that, we'll remind ourselves that the concentration of A minus is equal to the moles of A minus divided by the volume. Okay. Now the volume I just call V, and the same for let's just write that as the V. And here it's important to know so that we don't really know what the volume is. Look, we've got 50 centimeters cubed of ethanoic acid, but you're going to add some solid to that. So the new volume is going to be more than 50. You don't really know what it is, but that doesn't matter because that will cancel out. And so for HA, do the same thing. We want moles HA divided by the volume. So let's put that into this equation here. So we're going to get moles A minus over V, moles HA over V is equal to that. Of course, we're going to cancel those V's out, so they've gone. So we've just got the moles of A minus and the moles of HA now. Oops, didn't need to do that. Now we need to work out how many moles of ethanoic acid we've got. Moles of ethanoic acid, well, that's equal to the concentration of the ethanoic acid multiplied by the volume. The concentration it tells us in the question was, it was 0.8, and the volume was 50 centimeters cubed, so that's 0.05 dm cubed. So that's equal to 0.04 there. The H plus concentration, well, that is equal to the pH so 10 to the power of minus pH. 10 to the, which is 10 to the power of minus 3.9. Put that into the calculator, you get 5.28 times, what do you get? You get 1.259 times 10 to the minus 4. Okay, let's put in the numbers into this now then. So well, let's just rearrange that first. We're going to get moles A minus is what we want to find out, the moles of sodium ethanoate, Ka times moles HA over the hydrogen ion concentration, which was that. Ka, they tell us, is 1.74 times 10 to the minus 5. Moles of HA was 0.04 over the hydrogen ion concentration. Put that into the calculator, we get a value of moles of A minus equal to 5.528 times 10 to the minus 3. Of sodium ethanoate. Okay, now sodium ethanoate has the formula, the following formula, CH3 COONA. So the MR of that is equal to 82. Now we need to work out, change this number of moles of Na. It asks us to work out the mass, so we just do moles of sodium ethanoate. So mass of ethanoate is equal to moles times MR. 5.528 times 10 to the minus 3 multiplied by 82, which gives us 0.453 grams. That is our answer. Okay. Right, next question. Right, I'm just going to say here, that is a tricky calculation. Buffer calculations are probably the hardest calculations on the A-level specification. And if you want some practice on those, if you look at, that's my acid equilibria playlist there. So just do Davis A-level chemistry and then go to playlist. That's it. There's 16 videos in that playlist altogether. And these are the 3 that refer to buffer calculations if you want to have a look at those. Right. Okay, one of the systems controlling the pH of blood is the carbonic acid hydrogen carbonate buffer system. Okay, so here we've got carbonic acid. It's a very weak acid, dissociates into H plus ions and hydrogen carbonate ions. Explain how this buffer system helps to control the pH of blood when extra carbon dioxide is present due to strenuous exercise. So 3 marks. I think what we need to say is, right, extra CO2. Well, CO2 reacts with water to form carbonic acid in the blood. So you've got a higher concentration of carbonic acid. So that means that is going to dissociate according to this equation here. But because the hydrogen ion concentration doesn't change that much, because you have got you've got a lot of hydrogen carbonate in the blood, and that can react with the excess, with the extra H plus which has been made, and so that will lower the H plus concentration. So it's reliant on your blood having sort of a large reservoir of hydrogen carbonate ions in your blood. Okay. Right. Okay. A weak acid strong base titration curve we've got to draw here. Can we draw a titration curve for the addition of 100 centimeters cubed of sodium hydroxide with of 0.1 molar to 40 centimeters cubed of propanoic acid. Okay, so I've written this down here. Okay, and show the and the concentration to do. Well, this has got an original pH of 3. It's telling us that, so we've got to start off at 3. Right, just to remind ourselves here, we've got sodium hydroxide 100 centimeters cubed. We're going to add that. But we're going to add that to 40 of propanoic. Okay, now you can see that these are the same concentrations, and they react in a 1-to-1 ratio. So the end point of this titration is going to be at 40 centimeters cubed, which is just there on our graph. That's 40. So we want to draw the end point, something like, so this is the vertical part of the line there. Now, if you see, hopefully that I've chosen, you can see that I've chosen the midpoint of that line is not pH 7, it's alkaline, slightly alkaline. When you do a titration of a weak acid with a strong base, the endpoint is slightly alkaline. It tells us the pH starts off at 3, so we're going to have to start off there. So the first bit, you get a little inflection, and then it will go like that. Okay, tidy that up a bit. Right, and then when it's gone past the endpoint, then the pH will continue, but all the way up to 100, so it will just gradually rise up like that. Okay, so you want something like that. That's going to be the correct titration curve. Now, which bit demonstrates buffer action is when you've got a mixture of HA and A minus, which is of course in this bit of the curve. And you can see there, look, we're adding here, you're adding little bits of OH minus. What happens to the pH? It doesn't change very much. It goes up a bit, so resisting the change, but it doesn't change dramatically till you get to about there. And of course, then it will shoot up. But the red bit I've circled is acting as a buffer. And of course, if you remove the OH minus, in other words, if you add H plus, then the pH is going to go down a little bit, but not dramatically. It just goes down slightly. So it's buffering in that region there. Just to remind you here, so what do we need? A buffer, you need a mixture. You don't need to say this in your answer, I'm just saying it. A buffer is a mixture of a weak acid and its conjugate base, A minus. Okay, let's see what we've got. At this point, we've got more or less 100% of the weak acid, and we've got like 0% of A minus. At the end point here, it's the other way around, we've got 0% of HA, and we've got 100% of A minus. So in the bit I've circled in red, that's where you've got plenty of HA and plenty of A minus is acting as a buffer. Now, describe without calculation, how would you use your curve to determine the value of Ka for propanoic acid? Well, remember the half equivalence point. Half equivalence point, which is going to be at 20 here, just there. So I'll draw it in a different color. That's half equivalence point. And what you would do is you would go that across there, and the pH at half equivalence points, that is the pKa of the weak acid. Okay, so how would you find out the Ka? Well, Ka, how do you convert pKa to take Ka? It's the opposite, so it's 10 to the power of minus pKa. That's how you do it. So you find out the pH at this point, that's your pKa, put it into that equation, you've got it. How does that work? Well, of course, we've got H plus concentration. If you rearrange the Ka equation, we've got that. You don't have to mention I'm just saying this yet. Well, at half equivalence point, we've got equal amounts of HA and A minus. So AHA concentration is equal to A minus concentration. So that means those two things, they'll cancel out. H plus is equal to Ka. Take logs of both sides of the equation, we get pH is equal to pKa. So at half equivalence point, the pH is equal to pKa. Again, I've said more than you need to, but just to explain things a bit. Right. Question now about equilibria. Right. We've got sulfur dioxide and oxygen reacting to form SO3. The composition of an equilibrium mixture and at a total pressure of 2.4 atmospheres is shown in the table. We've got to calculate the value of Kp at this temperature. Okay, so let's do that. So first of all, I'm going to write down the expression for Kp. Kp is going to be equal to the partial pressure of the product SO3. And there's 2 moles of that, so it's going to be, we need to square that, divided by the partial pressure of the reactant SO2 and the partial pressure of O2. Okay, so that is our expression for Kp. Now, partial pressure of one of the components is equal to the mole fraction, and I'm going to use this little symbol for mole fraction, lambda. I'm going to use that, capital P, that is the total pressure. Okay, so we've got partial pressure of SO3 is the mole fraction of SO3 multiplied by the total pressure P. Right, so I'm going to substitute these the mole fraction P into the Kp expression. Okay, I'm going to do that now. So Kp is going to be equal to mole fraction of SO3 times P all squared, mole fraction of SO2 times P all squared, multiplied by the mole fraction of O2 times big P, the total pressure. I'm going to expand out those brackets there. So I'm going to do that here. So we get Kp, so Kp, small p, mole fraction of SO3, all squared, times total pressure squared, divided by the mole fraction of SO2, squared, pressure squared, multiplied by the mole fraction of O2, multiplied by the pressure. Now you can see that I can get rid of those 2 p squared terms by cancelling them out. So I'm going to get rid of them. Makes life a bit easier. Now all we need to do before we put our numbers in, we need to work out the mole fractions. Okay, so mole fractions, to remind ourselves. Right, okay. Right. So mole fraction, how do we do that? Mole fraction is equal to the moles of, let's do SO2, divided by the total moles. So the total moles, we're going to add that and that and that together, and that comes to 0.8. So the mole fraction of SO2 is going to be 0.016 over 0.8, which is equal to, nice round number, it comes out to be 0.02. Do the same for, so that's the mole fraction of SO2. The mole fraction of SO3 is going to be 0.772 over 0.8, which is 0.965. And the mole fraction of oxygen, 0.012 over 0.8, which is 0.015. Right, now put the numbers into our Kp expression here. Kp is equal to the mole fraction of SO2, so that's going to be 0.965 squared divided by 0.02 squared times 0.15 multiplied by the total pressure, which is 240 atmospheres. Put the numbers into the calculator and we get 64,700 atmospheres. That's the three significant figures. Right. What are the units? Well, it's atmospheres to the -1 is the correct unit, because look, look at this expression here. We've got two pressure terms on the top, so that's going to be atmospheres squared. And on the bottom, we've got atmospheres squared, but then we've got another one there for the oxygen, times atmospheres. That's equal to 1 over atmosphere. And of course, that's atmosphere to the -1. So that's our answer to that question there. Next one. Calculate the number of sulfur dioxide molecules present in this equilibrium mixture. Okay, so number of molecules is going to be equal to the moles multiplied by the Avogadro constant, L. So how many moles of SO2 did we have? We had 0.016 multiplied by 6.23 times 10 to the 23, which is equal to 9.632 times 10 to the 21 molecules. Right, deduce by referring to Kp how the number of SO2 molecules will change if more oxygen is added to the equilibrium mixture. Okay, right, now we know Kp is constant. The only thing that changes Kp is if you change the temperature, and we're keeping it constant temperature. That stays the same. Now, we add more SO2 molecules, that has got to increase. So in other words, so it's pretty obvious, to keep Kp the same, this must decrease. The partial pressure must decrease. Sorry, if I put the wrong way around there, because it said if you increase the oxygen, get rid of that, sorry. We've increased the oxygen moles, so we've increased the partial pressure of oxygen. So that means this value, the partial pressure of SO2, has got to decrease in order to keep the Kp the same. Okay, an equilibrium exists in aqueous solution between the chromate 6 ions and the dichromate ions. Okay, so there we've got them. Okay, so we've got chromate 6 and dichromate. Explain any change in the position of equilibrium. A few drops of sodium hydroxide are added. Okay, so look, if we add OH minus, okay, the OH minus is going to react with the H plus to neutralize it, form water. So that means we are going to lower H plus concentration. So Le Chatelier tells us the equilibrium will move to the left in order to make more H plus, to oppose the change. So that means the equilibrium will move to the left, and you're going to get more chromate. Incidentally, you've probably done this experiment. This stuff is yellow. The chromate 6 is yellow, and the dichromate is orange. So if you've got an orange solution of dichromate, which is the way around, sorry. That was wrong. So this one is yellow. And this one is orange. So if you have an orange solution of potassium dichromate, which you usually do, and then you add a bit of alkali to it, what happens is you make this equilibrium go backwards. The solution will change color from being orange to yellow. And then if you add some acid to it, you can make it go back orange again, because if you add acid, it's going to go the other way. Again, it doesn't ask you that, I'm just saying it. Okay. Okay, the last question then, the equilibrium reaction between hydrogen gas and an oxide of iron is given below. Now, this is a heterogeneous equilibrium. That means that not everything is in the same phase. And look, we've got iron oxide solid, and we've got iron as a solid. The concentration of solids are constant, so they don't appear in equilibrium expressions, so we ignore them. So the correct value for Kc is going to be this one here. So you've got 4 molecules of water, so it's H2O to the power 4, and you've got 2 molecules of 4 molecules of H2, so it's H2 to the power 4. Okay, and that is the end of that paper.